Hello and welcome to another session in this IBDP MAI course. So today we are going to talk about the Poisson distribution. We will cover all the concepts in this Poisson distribution. So let's start with why do we need this Poisson distribution? What are the conditions under which we can apply this Poisson distribution? Okay. In independent events where the probability of success outcomes is very small, then this Poisson distribution is an excellent estimator of the binomial distribution. Generally, however, for the Poisson distribution to be suitable, the rate of occurrence must be constant, and the number of times an event occurs within interval of time should be proportional to the length of interval. Okay, here you can use this formula also for finding the probability of exactly r successes using the Poisson distribution is given by m raised to the power r e raised to the power negative m divided by r factorial, where m is you can say average, mean, or variance also in this case. Remember, for Poisson distribution, mean and variance are same. Now, you can also find the value of this by NP, where N is total number of trials and P is probability of success in one independent trial. So later we will see how do we use the calculator to calculate the probability for exactly or the continuous values. Like there are two options in the calculator. One is Poisson PDF, which we use if they says find the probability of exactly R successes. And we can use the Poisson CDF if they says there is a bound. Like we have to find the probability from X lying between A to B, then we can use this Poisson CDF. Okay. So let's start with the question. The question says a spinner is designed to produce one of the two outcomes using the circle divided into two equal parts, but quite unexpectedly, it appears that the spinner needle lands on the dividing line between the two outcomes with a small probability 0.001. Now it says what is the probability that in 3000 spins, the needle lands on the line 4 times instead of landing on one of the regions. So we can solve this problem by using binomial, or we can solve this problem by using Poisson as well. I'll show you how. So let's start this with binomial first. So for binomial, we need n number of trials, which is 3000 in this case. Probability of success, it is 0.01 already given, 0.001 already given to us. Now we need the success. How many? 4 successes. Then the probability for exactly 4 successes using the binomial trials is given by NCR, which is 3000 C4, 0.001 whole raised to the power 4 multiplied by this 0.999 raised to the power 2996, right? This is our 1 minus p. This is p and this 4 is r. Okay, and this is n 3000. Now, if you use your calculator, you can get the answer. It comes out as 0.1681 something. Okay, 0.1681 something. So you can also take 0.168 only. Now, you can also use the calculator for finding the binomial by binomial PDF in this case for 3000 trials, and the probability of success is 0.001, and we need the probability for exactly 4 successes. That also gives you the same thing, 0.168. Now that's our answer using the binomial trials. Let's find the answer with the Poisson distribution as well. So for Poisson, first we need that parameter lambda, which is the mean. We can calculate it by n times p. What is that? N 3000 multiplied by p, which is 0.001. So we got the value of lambda as 3. Now we are looking for exactly 4 successes. You can use either that formula or you can use the calculator because it is allowed in MAIHL course. So let's apply the Poisson PDF here for 3 and 4. When you apply this, you will get same answer, which is 0.168. Okay. It means, yes, we are getting the same answer here using either binomial or using the Poisson. Actually, The thing is, the probability of success is very, very small. That's why we are looking for the Poisson distribution. It's a best estimator at this point. Okay, let's do some more thing on this Poisson distribution. The thing is, the Poisson distribution as a probability model for the rate of occurrence, and always remember the following points, like all the events are independent to each other. Yes, I already told you these things. Like event occurs at a constant average time and cannot occur simultaneously. And also remember, we are counting the number of occurrences. We are not measuring the continuous variables. Okay. Let's look at another problem. It says the number of phone calls received in an hour C by an IT helpline follows a Poisson distribution with the mean 7.3. So in this problem, they gave us the value of mu, or you can say 7.3, which is also the variance value, and you can call it lambda as well. Now, it says find the probabilities for the following events. What are that? Exactly 6 calls. It means we are looking for Poisson PDF. For how many successes? 6 successes, where 7.3 is the value of lambda. So put these values, you will get your answer. In the second part, it says more than 4, means starting from 5, you can say, but not more than 8. So we are looking for Poisson CDF in this case, right? And here your lower bound is what? 5 and upper bound is 8. So you can also use this 7.3 between 5 to 8. So if you use your calculator, again you can get your answers. Okay, let me show you how. So basically the value of lambda in the A and B part is given by 7.3. So we are looking for exactly 6 successes, and let's use the calculator for Poisson PDF to get the answer for the first problem, which gives us 0.1419, and we can say it is 0.142 to correct it for 3 significant figures. Similarly, from 5 to 8, because we need more than 4 and less than equal to 8. So that gives us Poisson CDF for 7.3 from 5 to 8 comes out as 0.54188. We can write it 0.542. Okay. Third part. It says at least 15 calls are made in 3 hours interval. Remember this, 3 hours interval. So what we can do, instead of taking x this time, our random variable is 3x this time. Let's call it y. Y is equal to 3x. And you already know for this 3x, the mu or the mean value changes by 3 times of the old. So mu of y for the new will be same as 3 times mu of x. So our new lambda y for the C part will become 3 times of that 7.3. Clear? So this time our lambda value is going to be this 21.9. So in the C part it says at least 15 calls. At least 15 calls means we are looking for x value, right, which is greater than 15 or equal to as well. So apply it with taking lambda as 21.9 and use the Poisson distribution in your calculator. For either you can use Poisson CDF. 21.9 is the value of new lambda. From 15 to a very, very large number, you can take 1000, 2000 or whatever you want. There is no problem. Or you can also calculate 1 minus the probability that it is less than 15. So you can start with your lower bound from 0 to upper bound as 14 and subtract that probability from the 1. That also gives you the same answer. So in both the cases, we are getting the same answer, and hence our answer is 0.950. I hope you got this. Okay, next one. X is a random variable that follows a Poisson distribution with the mean 2.5 by considering the mean and variance of 2x. Explain why 2x does not follow a Poisson distribution. Do you remember that I said in the beginning the mu and sigma square, variance and the mean, must be same for applying this Poisson distribution. So initially it says x is our random variable where the mean is given by 2.5. So initially we had first case where mu or sigma square both are 2.5. But later you changed it to what? 2x. So the new mean will be 2 times of the old, which is 2.5 times 2 means 5. But sigma square will change by what? 2 squared times. 2 squared times 2.5. What is that? 10. So can you see? For our new random variable 3x, these two are not same. So Poisson distribution cannot be applied here. That's the reason. Okay, because mu becomes a times the old mu, right? So in this case, we cannot apply the Poisson distribution because mean and the variance are not same. Next one. If x follows a Poisson distribution with mean 3.1, then find the probability that x less than equal to 3. So either use your calculator, right, for Poisson CDF. So put Poisson CDF here. The mean is 3.1. The lower limit, what is that? 0, and upper limit is 3 because you are looking for the probability from 0 to 3. So that gives me my answer for Poisson CDF. Lambda is 3.1, lower bound 0, upper bound 3. The answer is 0.6248, or you can say 0.625. That's it. Next problem. The number of bees observed each hour in a garden follows a Poisson distribution with mean 2.1. Remember this. This is our first mean. Let's call it lambda 1, which is 2.1 here. The number of butterflies observed each hour in the same garden follows a Poisson distribution with mean 4.3. So this is our lambda 2, let's say, which is 4.3. Now it says assuming these two variables are independent, that and the bees and butterflies are the only insects observed. So for the bees, we have lambda 1 2.1. For the butterflies, we have lambda 2, which is 4.3. It says both are considered as now insect, and find the probability that more than 8 insects are observed. So what we are looking for? We are looking for Poisson, right? Poisson CDF. It says probability more than 8. So more than 8, we need lambda value, and it starts from 9 to there is no end. You can put any large value, let's say 2000. Okay. But what about this lambda value now? So this lambda value for the Poisson distribution, two Poisson distributions are given. So lambda will be given by lambda 1 plus lambda 2, which gives us 2.1 plus 4.3 makes 6.3. So that's our new lambda value, 6.3. Now use your calculator and get this value, which gives us Poisson CDF lambda value as 6.3. 9 is the lower bound, and upper bound you can take any large number, or you can also use 1 minus Poisson CDF for 6.3. Lower bound is 0, upper bound is 8. That also gives you the same value. So here you can find this value and get your answer. Let me put this. 6.3 0.81476, or I can say 0.815. That's the answer. Okay, you can use either method to get your answer. Okay, so now what we have covered so far, we have seen this Poisson distribution. Its mean and variance both are same, right? Recognizing situation in which the appropriate to use the Poisson distribution as a model. Yes, we have seen probability is very less, and we are doing it for a interval of time. Know that the Poisson distribution, the mean is equal to variance. Yes, it is important to know this thing. Using the calculator to find the probabilities using this Poisson distribution by PDF and CDF, both covered. Also, sum of two independent Poisson distribution has a Poisson distribution, as we have seen in this case of butterflies and bees, where we added them up to get a new lambda value, right? So that's also done. Now I'm giving you few practice questions. You can try these questions by yourself, and I'll see you all in the next session. Thank you for watching this. See you. Keep watching, keep learning.